Hello friends, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with chemistry, and this is the lecture of IR spectra and lecture number 31, in which I will explain you factors affecting C double bond O vibrations. So in previous lecture I gave you in brief which are the factors affecting C double bond O vibrations. The very first factor which we'll discuss is physical state of sample. So if we take examples of amide, primary amide, which is CONH2 group, then we will observe band at 1650 centimeter inverse if it is in solid state, and it can be 1690 centimeter inverse in dilute solution. If we can take secondary amide, the structure is RCONH R or maybe R dash, whatever. Okay, so here the band appear at 1640 centimeter inverse in solid state, and at 1680 centimeter inverse if you take in dilute solution. So this is the difference of state. Well, here also we will discuss band in anilide group NHCOCH3, in which C double bond O appear at 1700 centimeter inverse, which is in solid state. We'll take example of tertiary amide, which is RCO and R2. There are two alkyl groups attached to nitrogen. The band at 1680 to 1630 centimeter inverse, and here there is no effect of physical state. Next factor is resonance. Or we can say conjugation effect. Okay, let us take example. Suppose we take this compound C double bond O acetone. Here C double bond O stretching appear at 1720 centimeter inverse. Now in case of aromatic ketone, here due to conjugation of double bond, resonance appear and the band appear at 1690 centimeter inverse. If we take this example, in which there are two aromatic rings attached to C of C double bond O, more conjugation appear and the band appear at 1662 centimeter inverse. So this is clearly showing that resonance stabilizes the charge, which leads to decreasing absorption. So remember, due to resonance or conjugation, there is always reduction in frequency of bands. Okay, we'll take few more examples like this compound aldehyde. Okay, and in this case C double bond O stretching appear at 1730 centimeter inverse. And if we take this one, benzaldehyde, then it is at 1710 to 1685 centimeter inverse. So because of resonance, the C double bond O stretching decreases. Now we take acetic acid. Here the C double bond O in acetic acid appear at 1720 to 176 centimeter inverse, while in case of benzoic acid C double bond O appear at 1710 to 1680 centimeter inverse. If we take ester, then C double bond O will be at 1750 to 1735 centimeter inverse, while in case of aromatic ester, which will be like this, then the band at 1730 to 1715 centimeter inverse. Well, here also we have another kind of aromatic ester which is like this. Then this will be at 1770 centimeter inverse. Okay. Next is cyclic ester. Here we will have C double bond O stretching at 1720 centimeter inverse, while in this case here you will see that double bond is in conjugation. But if you take this example where there is no conjugation between C double bond C and C double bond O, then it is at 1760 centimeter inverse. So these are all examples in which you will find that due to resonance, you will see the change in C double bond O stretching. One more example we'll take of amide. Here, because this lone pair transfer over here and this pi bond electron also transfer to oxygen, there will be bending appear at less than 1700 centimeter inverse because of this resonance. And here you will see that this compound where conjugation takes place, and it will be nearly 1690 to 1640 centimeter inverse. So because NH2 is electron donating group which resonate and reduce the strength of C double bond O. Therefore, frequency decreases. This is called plus M effect. So here we can say that plus M effect dominates over minus I effect, and therefore we'll see the mainly the effect of plus M. Next one is inductive effect. With reference to inductive effect, there are two types of functional groups. One is called plus I group, in which frequency decreases, and if it is minus I group present along with C double bond O, then frequency increases. Best example is formaldehyde. Here both sides are hydrogen of C double bond O, and in this case C double bond O is at 1750 centimeter inverse. Now in case of acetaldehyde, where there is methyl group which is plus I group over here, and therefore band appear at 1730 centimeter inverse because of plus I group. Okay. Now if you put both plus I group on sides of C double bond O, that is acetone, then it will be still less and will get band at 1720 centimeter inverse. So here is seen that plus I group reduces polarity of C double bond O, and therefore frequency decreases. Okay, few more examples. We take this compound, acid, and here you know that C double bond O is at 1720 centimeter inverse. Now with CH3 we replace one hydrogen by Cl, so this is minus I group, and that will change the frequency of C double bond O to 1735 centimeter inverse. If there are two chlorines attached to carbon, alpha carbon of acetic acid, then you will get more higher band at 1762 centimeter inverse and so on. So this way we can see the effect of minus I group. One more example. Here we will see acid halides like acid fluoride, in which C double bond O is appearing at 1869 centimeter inverse. Now when fluorine is replaced by chlorine, acid chloride, the band appear at 1810 centimeter inverse because minus I effect decreases. In fact, if you take Br over here, acid bromide, then the band at 1790 centimeter inverse. Okay, so this way you can see the effect of minus I group. So it's very clear that minus I group increases polarity of C double bond O, and therefore frequency increases. Okay, so this is very clear about plus I group and minus I group. So these are the three main factors affecting C double bond O. There are two more that I'll explain you in next lecture. Thank you so much.